this video, we will be servicing the lubrication system in this 2008 Hyundai Elantra. This video is broken up into 4 primary parts. First, we will take a sample of our current motor oil and send this off to get it analyzed. Next, we will drain the oil and replace the filter. After that, we will install an easy oil drain valve and refill the oil. And lastly, we'll take a look at our oil analysis results over the past year on this oil. In order for me to take a sample of oil from my existing engine oil, I need to have an oil analysis pump, I need a length of tubing, and I need my oil analysis kit. To gain access to the engine bay, we first need to pop the hood. But to pop the hood, we need to use our hood release latch, which is located inside the vehicle through the driver's side door. After releasing the safety latch, we can open our hood. Taking a look in our engine bay, there are 2 key items that we need to locate. First is the engine oil fill location, which is located on the engine block towards the top. Secondly, we need to locate the oil dipstick. This will allow us to both take our sample and it allows us to check the level of our engine oil. If we take a closer look at our oil fill cap, we can see that there is an icon of an oil can, so we know that this cap has to do with oil. We also see there is an identified mark of SAE 5W20. This indicates the viscosity of oil that this particular engine needs. If we take a little bit closer look at the engine oil dipstick, we can see that the top of it is identified with the markings ENG oil. This gives us a good indication that we have found the correct dipstick. In order for me to take a sample of my existing oil, I need to size my tubing to the correct length. To do this, I'm going to remove the dipstick, and I have a rag here to clean off the end of it. Using the dipstick as a measuring guide, I'm going to measure a length of tubing that is about 6 inches longer than the entire length of the dipstick. Next, I'm going to again use my dipstick, kind of like a measuring tape, and I'm going to put a mark on my tubing that will indicate the same length as the dipstick. After that, I can install my tubing into my oil analysis pump and tighten that down. And after our tube has been installed, we can install our collection container. Now that we're ready to take our sample, we can insert our tubing into the dipstick location, and I'm going to insert this all the way down to that black line that we had made. This essentially simulates the dipstick going down into the engine, reaching our reservoir of oil in the bottom. And with a few pumps, we can pull our engine oil sample. And once we have filled our collection container, we can use a rag and remove our tubing. And then very carefully you can remove the collection container and cap that. After disposing of the tubing properly, we can fill out our paperwork. This video does not go over the specifics on filling out the paperwork. For more information, you can watch my oil analysis sampling video. And don't forget to reinstall that dipstick before you continue. After having taken my sample for oil analysis, I am ready to continue on with my oil change procedures. To do this, we need to remove all of the old oil and change the filter. A couple things that I do prior to starting the oil change to set up the vehicle for, number one, safety, but also ease of access. I have installed rhino ramps underneath the front tires, which will help elevate the front of the vehicle. I have wheel chocks on the back of the vehicle on both sides. I have my emergency brake on, which will lock the back tires. And then as one additional measure, I have installed safety stands underneath the vehicle, just in case the other three things I've done fail. Underneath the vehicle, we need to locate the oil pan and the oil drain plug. The oil pan is typically located below the oil fill location. While under the vehicle, we also want to locate the oil filter. The oil filter is a canister type looking cylinder and is screwed onto the engine in a location that is typically near the oil pan and in the same vicinity as the oil plug. Next, I'm going to place a drip pan underneath the location of my oil plug so I can catch all the oil. Using a 17mm wrench, we can loosen the drain plug. Now, it does help if your engine is slightly warm so the oil will flow better. After we have drained out all of the oil, we can reposition our drip pan underneath the oil filter and we can remove the oil filter. After having pulled the old oil filter off of the vehicle, we need to double check and make sure that the rubber ring came off with the filter and is not stuck up inside the engine. If your filter does not have that rubber ring on it, make sure you check up in the engine and make sure that's removed off of the engine. If you install a new one and there's two rubber rings on it, then you'll leak oil all over the place. For this vehicle, I use Amsoil's 100% synthetic 5W20 Signature Series motor oil. I'm going to use a little bit of this in the process of installing my new oil filter. If I remove my new oil filter, I noticed that this one also has a rubber ring on it, or a gasket. If I put the filter on with the gasket dry as it comes out of the box, there is a chance that it won't seal properly. So I'm going to take just a little bit of my new oil and I'm going to lubricate the rubber ring on my new filter. Now, you don't want to do this with your old oil that you pulled out of your vehicle, because essentially you're just rubbing dirt all over that rubber ring then, because that old oil is dirty and contaminated. When installing the oil filter, it is important that you do not over tighten the filter or you could damage that rubber seal. You also don't want it too loose where oil is going to squeeze out. A good rule of thumb is to tighten it hand tight and then go just a little bit more so that it's good and snug. It's not going to come off very easily, but the next time you do an oil change, you shouldn't need to use any type of wrench or anything to get it off. You want it tight, but not too tight. Normally at this point you would reinstall the oil drain plug. However, for this particular vehicle, I will be installing an easy oil drain valve. I saw this on the internet and it intrigued me, so I thought I'd give it a shot. If we take a look inside the package, we have a different kind of oil plug. This particular oil plug has a ball valve built into it, so in theory you never have to remove the plug. You just turn the ball valve and your oil comes out. Now, although the end of this valve has a rubber O-ring, I have read online some complaints from people that say that it still oozed or leaked just a little bit out of that seal. Could be that they just didn't install it correctly, they over tightened it or something of that nature. Now, since I use Amsoil's Signature Series motor oil, I only change the oil once a year. And if you're interested in getting more information on the research behind that, feel free to send me a message. But because I only change it once a year, I don't want to install this valve and then have it start oozing or dripping and then have to do another oil change. That would defeat the purpose of using a high quality oil to have to do oil changes all the time. So to remedy this possible issue, I'm going to be applying a small amount of Permatex's Ultra Black gasket maker, which is a gasket maker that is designed for oil applications. And given that this is on our lubrication system, where it may come in contact with oil, this is an ideal product to use in conjunction with that rubber O-ring that is already installed. Now, you will want to read the package and follow the directions for the Permatex gasket maker. There is a wait time between application and installation and refilling the vehicle. Once installed, you can give it a quarter turn to snug it down. This is one thing that you do not want to over tighten though. At this point, we should be ready to reinstall the new oil. We have removed the old oil filter, made sure that rubber ring was off, installed a new oil filter that has been lubricated. We drain the oil out. We replace the plug with our easy oil drain valve. And the other thing I need to do is double check to make sure that drain valve is in the off position or the closed position before I start filling up the engine with oil. This particular vehicle takes 5W20 motor oil. We can verify this with the oil cap. You could verify this with the owner's manual, or you can also look online. This vehicle has been identified as taking just a little bit over 4 quarts of motor oil. I will be using Amsoil's Signature Series 5W20 motor oil. Locating our oil fill cap, we can remove that and install a clean funnel. You don't want the funnel to be dirty because we just took out dirty oil and we don't want dirt getting back into the engine. And after 4 quarts have been installed, we can put the cap back on. I like to start the engine for about 15 seconds. This will get the oil flowing through the engine and will fill up the oil filter. At this point, I'm ready to check my engine oil just to make sure I'm at the full level. However, the vehicle is still on the rhino ramps, which means the vehicle is sitting at an angle and not on a flat surface, so it's not going to give me an accurate reading. So I'm going to remove my wheel chocks, my safety stands, the rhino ramps, and get on a level surface before checking the oil. And when checking oil, we want to first clean off the dipstick with a rag, reinstall the dipstick into the engine, and then pull the dipstick out. Now, it may be difficult to tell the oil level because the oil is new and it is a translucent brown and kind of difficult to see. We want to make sure that our oil level is between the low and the full, ideally a little bit more towards the full. This particular one, we are sitting up near our full indicator. Typically the distance between the low dot and the full dot is 1 quart. However, we're sitting up right where we want to be at. Lastly, we can reinstall the dipstick, double check underneath the vehicle to make sure there isn't oil profusely leaking from somewhere, and take it on a test drive. After a week or so, I received my oil analysis results. At the top of my analysis report, I have the account information, I have the component information for the particular vehicle or equipment that the analysis was conducted on, the sample information for when the sample was taken, there's some filter information, miscellaneous information, and the product information is the particular type of motor oil that this analysis was done on. Having this information allows a baseline value for what the oil should be compared to what the oil is now. For right now, I'm going to skip the comments section and move down to the actual results. Now you'll notice that there are multiple results. The NL line is a new lube sample, which is a sample that is directly out of the bottle. This is the line that I will be using as my baseline reference for comparing my current sample. Sample number 4 is the sample that was taken during this oil change service. The additional samples 1 through 3 were taken from 2015 through 2017. Moving back up to my wear metals, I want to take a look at the current wear metals that are in the oil sample compared to a new sample. Anytime there is a wear metal element identified, it would suggest that there is some type of wear that is occurring inside of the engine. The only items that indicated there were contaminants were iron, aluminum, and copper. In general, these values are not reason for concern. It was not identified by the oil analytics scientists that these were warning areas, but it is worth taking a look at the history of these particular values. Having 1 parts per million of copper is pretty insignificant, and that is pretty much in line with what I have seen in the past. The iron and aluminum values show a small spike from the previous years, and ironically enough, about 1 month after this test was taken, the oil pump in this vehicle failed, which in turn led to the replacement of the engine in this vehicle, which was still covered under warranty by Hyundai. Perhaps the spike in iron and aluminum could have been a warning sign or precursor to the oil pump failure. However, the values were not high enough to warrant any concern at the time of the test. We're next going to take a look at the contaminant metals and multi-source metals. The contaminant metals are elements that are an undesirable addition that somehow has found its way into the oil. The multi-source metals are metals that are coming from a variety of locations. It could be a contaminant, it could be a wear element, or it could be an additive that was placed into the oil originally. Values shown in white indicate normal conditions. Values in green are on the normal side but nearing the abnormal. Values in light orange or kind of a yellowish color indicate an abnormal condition. Values in dark orange constitute an abnormal condition leading to a critical condition, and values in red indicate a critical condition. Taking a look at the results, I can see that silicone is a little bit above what it has been the previous years. It still falls within the normal range, but there is a little bit of a bump up. If I take a look at sodium, I can also see a little bit of a bump up from the previous years, but it is falling within the normal range. Potassium appears to be in line with the previous years. Molybdenum is a friction modifier additive, but it can also be an anti-wear coating or insert on some piston rings. That is why it falls under multi-source metals, which are metals that could be coming from different sources. My molybdenum values fall within the normal range. It appears to be fairly in line with the previous values. Manganese is an alloy used in certain steel applications, as well as a component of gasoline additives. In this particular vehicle, I do use a gasoline additive. However, I have used that same gasoline additive for the life of the vehicle. So to suddenly see a jump to 87 parts per million does issue some concern. However, in light of my iron and aluminum values being elevated, it is possible that this manganese increase is due to some type of metal wear inside of the engine. The last multi-source metal that we will take a look at is boron. Boron is a coolant additive, and it is also a lubricant oil additive. If this were to be a contamination from the cooling system, you would see the boron levels spike above the baseline levels. Given that my baseline levels are 212 parts per million, and that has been depleted down to 24 parts per million in this sample, it is clear that this particular source is from an additive that was originally in the lubricant. Boron and borates have been used since the mid-1970s as part of the additive packages to various lubricants. Nowadays, it is not uncommon to see lubricating oils and greases containing these borates. They are used as anti-wear and extreme pressure additives. Essentially, what they do is they coat the surface, so it reduces the chance of metal-on-metal wear inside of the engine. On a molecular level inside of the engine, you have what is known as van der Waals forces. This creates an electrostatic attraction between the molecule of oil and the sidewall of your engine or whatever component that it comes in contact with. Boron, or the borates, are essential in creating this static cling type effect. And over time, those additives, boron in this case, will drop out, as we can see from the values where we started at 212 parts per million, and they have dropped out and they are down to 24 parts per million. Effectively, this indicates that the life of this oil is quickly nearing its end. Next, we will be taking a look at the additive metals that are in this oil sample. These are the components that were engineered as part of the original oil formulation. In other words, these metals should be in there if it was a part of the original manufacturer's formulation of the oil. Magnesium is an additive metal that neutralizes varnishes and sludge. In addition, it helps maintain those in a soluble state inside of the engine. Our values over the course of all of these samples indicate that the values that we have are in line. The purpose of calcium is much in the same as was the purpose of magnesium. Our values are well within the acceptable range. Phosphorus and phosphates work very similar to boron in its ability as an anti-wear and extreme pressure additive. Our values look very good. Zinc is used as an anti-wear, extreme pressure, and antioxidant additive. It is the most commonly used anti-wear additive in motor oils. It is a part of a larger additive package called ZDDP. Again, our values look just fine. I want to now jump down and take a look at the fluid properties for this motor oil sample. Taking a look at my total base number, I can see that those values have been identified as high on the abnormal scale, even into the critical area on our scale. Generally speaking, the higher an oil's total base number, the better its ability to neutralize contaminants such as combustion byproducts and acidic materials. TBN is a measure of alkaline additives in the oil. Higher TBN oils are able to neutralize a greater amount of acidic materials, which results in improved protection against corrosive reactions and longer oil life. TBN levels decrease as the oil remains in service. When the level reaches a point where it can no longer protect against corrosion, the oil must be changed. Oils that are formulated specifically for extended drain intervals typically will have elevated TBN values to ensure proper corrosion protection for the duration of the extended interval. In general, Amsoil engineers their oil to have very high TBNs, which allows them to neutralize acidic contaminants and keep them in suspension to prevent corrosion for longer periods of time. Although my TBN values for each of the samples I've taken are in the abnormal to critical range, this is normal as this oil is run on extended drain intervals. The oil is only changed once per year. So these values are what is remaining as far as TBN is concerned for oil that has been running in an engine for an entire year. It also indicates that after a year, the TBN is essentially depleted, thus the oil needs to be changed. Given that there is a small amount of TBN remaining, this oil could theoretically actually be run for another month or two. The next thing we'll take a look at is oxidation. Oxidation is the interaction between oxygen molecules and motor oil molecules. This is a natural occurrence that leads to chemical breakdown. Just as oxygen causes a cut apple to brown or exposed metal to rust, it breaks down the base oils and reduces the motor oil's effectiveness. Oxidation can lead to increased oil viscosity, which negatively affects energy efficiency. It can also cause the formation of harmful deposits and sludge. Lubricants for internal combustion engines are exposed to severe oxidative conditions, particularly in the upper part of the piston ring and the cylinder liner zone, where maximum temperatures can exceed 250 degrees Celsius in a passenger car engine and even over 300 degrees Celsius in a heavy-duty diesel. In these areas, there are thin oil films. We talked about this with the van der Waals forces that are exposed to blow-by gases. These blow-by gases are generated in the combustion chamber. These high temperatures and the reactive blow-by gases lead to rapid oxidation of the thin oil film. Our values for oxidation are well within the normal range and are of no concern. Nitration is of concern in engine oils, particularly natural gas engine oils. Heat can cause atmospheric nitrogen and oxygen to react, forming nitrous oxides. These nitrous oxides interact with the lubricant by creating organic nitrates or being picked up as either soluble or insoluble nitrous compounds. Nitration can cause premature thickening of the engine oil, and common causes could be inefficient exhaust of the combustion products, improper air-to-fuel ratio, low operating temperature, or even leaking piston seals. Our values from all of our samples fall within the normal range. The viscosity is the oil's resistance to flow, and as we previously talked about, there are a lot of elements that go into determining viscosity as far as why it may increase and why it may decrease with the types of contaminants in the oil. After running this oil for an entire year, we have maintained pretty good viscosity. I'm going to jump back to my comments section that I skipped earlier. These comments are thoughts that the oil analysis scientist felt were important to get across. First, it is noted to monitor the drain interval and equipment operating temperature, which is what I do because I do run extended drain intervals in this vehicle. It is also noted that the base number is significantly low, and we talked about that, how the base number started really high. The oil has been run for a year, so it has depleted that base oil value to the point where it is currently low. It was then noted that the silicone is at a minor level. We also talked about that previously. It was noted that the viscosity is slightly high, although it did fall within the normal range, and they provided some reasons for that, which could have been contamination, oxidation. It was suggested that perhaps the viscosity grade was misidentified. Additionally, it was noted that if you add a different viscosity grade, it might throw off that number just a little bit. The remaining comments indicate that they have noted that I did a fluid and filter change, which would correct any of these abnormal values, and that no further maintenance is required at this time. The overall report, taking into account all of this information, it is identified that this oil, after running for an entire year, is in the upper abnormal range, which means that it is nearing the end of its life. The data that we have seen reflects that, as well as the manufacturer suggests replacing the oil at the 1 year mark, which is what was done in this vehicle.